Okay, so the first category for ways to stop memory safety vulnerabilities is to use a language that doesn't have memory safety vulnerabilities. It's almost so silly when I say it out loud, but this is actually a very effective way to stop vulnerabilities. Use a programming language that is safe. So some programming languages, by design, will check bounds for you. So for example, Java, Python, Go, these are languages that have built-in bounds checkers. When you define an array of size 5 and you try to access item number 6, the program will simply say no, and it will not let you access item number 6. So some languages are designed like that. C is not one of them. C is a language where if you define an array of size 5 and you ask for item number 6, C will gladly let you access that item even though it's out of bounds. So memory-safe languages, by design, the people who built the language added automatic bounds checking, and so these languages do not have memory safety vulnerabilities. All the memory safety vulnerabilities we've talked about have to do with writing past the end of an array, and if your language simply doesn't let you write or read past the end of an array, then memory safety vulnerabilities just don't happen. So all you really have to do to stop memory safety vulnerabilities is to pick any one of these languages that actually check bounds for you. And there's so many to pick from. In fact, the majority of memory languages or programming languages out there are memory safe. Really, the only ones that we can think of that are not memory safe are C, C++, and derivatives like Objective-C. So as long as you don't use one of those, you don't have to worry about any of this stuff. How nice is that? You can just ignore all this stuff, program all you want, knowing that attackers will not be able to write out of bounds. And this is the most robust defense against memory safety vulnerabilities, because if you use a language that actually checks bounds, these things just don't exist. This vulnerability is not there. And it's one of the only times in this class where I can tell you that there's a defense that works 100% of the time. If you use a language like Java or Python or C#, you are defending against 100% of vulnerabilities because this type of attack just doesn't exist. You actually went and solved the fundamental problem. So building off of this, the follow-up question you probably have is, well then why the hell do people still use C? So one reason that people like to bring up, if you ask around, is performance. So there's an argument that, well, C is not safe, but it's really fast. So we have to do a trade-off between the fact that it's really slow, or really fast, sorry, and the fact that it's not secure. And so, for example, Java, because it's a memory-safe language, some people argue, well, it actually has to do some extra tracking of memory and bounds checking, so it adds a little bit of a delay, whereas in C and C++, which are not memory-safe, memory management is as fast as it can possibly be. So this is an argument that some people really abide by, and if you believe in it, that's totally fine. But nowadays, newer languages have started to challenge this notion. So first we called it performance, but really it's kind of a myth. So if you think about your everyday programming, this is kind of our argument for why performance is not really that big of a reason. If you think about your everyday programming experience, writing code for assignments, for work, for, I would say, 99% of applications, the difference between using something like Java and something like C is not really noticeable. So for example, if you're writing code for your projects and you write it in C or you write it in Java, okay, one of them might be 10 milliseconds slower. Are you really going to notice a 10 millisecond difference on the autograder? I don't think so. And so maybe that 10 milliseconds is totally worth the extra security you get from using a memory-safe language like C. So there are some exceptions here. For example, operating systems have to be really fast. If you work at a very low level, maybe you do have to work with something like C. So there might be some exceptions. But maybe more fundamentally, I don't think there is a trade-off between security and speed. So historically, this might be true, that to add extra bounds checking, you have to waste some extra time, so the languages that are safer are slower. But nowadays, there are a lot of alternative languages that are as good as it gets when it comes to performance, but also memory safe. So the one that everyone likes to cite nowadays is Rust. Maybe if you watch this video like 50 years from now, there's a different language that's popped up. But the fact is, there are languages out there that are extremely fast, basically as good as C, and also memory safe. So if you can have both, what is the reason between trying to do a trade-off between security and performance? You should really just pick the languages that give you both. So while if you asked this question 10, 20 years ago, people might have said there was a trade-off, I think nowadays there really isn't that much of a trade-off. You should just go pick one of those languages that is fast and also secure. Why not have both? So maybe another kind of even more high-level fundamental philosophical reasoning here is that if you waste your time programming in something like C, you're going to have a lot of extra headaches trying to debug memory safety vulnerabilities. So if you're trying to improve performance in terms of how many lines of code you can churn out per day, maybe using a memory safe language is faster. It saves you time from debugging and fixing bugs, but that's kind of a very opinionated point. It's OK if you don't agree with it. Maybe one more thing that I would point out is that even if you use a language that is slower, like, say, Python, those languages often have libraries that plug into faster languages. So you might say, I don't want to use Python because it's so slow, but Python has libraries like NumPy that actually plug into an underlying C library. And so that's another way of using a memory-safe language, but also getting performance. You just plug into libraries that are written in really fast languages like C and Rust. And one more reason I can identify for why memory safety vulnerabilities still exist, because if it's not for performance, we've just debunked the myth that there's a trade-off between performance and security. Well, another reason why so many memory safety vulnerabilities still exist is legacy. Turns out, over the 100 years or so that programming has been a thing, has it been 100 years? I don't know. Maybe it will be in the future. But turns out people have written a lot of code in C over the years. And if someone hands you a big project in C, you have two choices. You can either rewrite the entire project in something safe like Rust, or you can just keep writing code on the existing code base. And guess what almost everyone does? They keep writing on the existing code base because it's easier. So if you join a company and all the code is in C, you are probably not going to rewrite all of the company's code in something like Rust. You will probably just continue contributing in C.